Now we are going to consider the frequency transmitter and the frequency receiver and how they are transmitting and what they are transmitting and what they are receiving. So if we talk about that message signal x of t is provided, and here carrier signal AC omega ct plus phi is applied here. So here we can write phi, and so when it is applied here, then this we get that frequency modulated signal or phase modulated signal will become, or we can say roughly that is angle modulated signal will become, that is xc of t is equal to AC cos omega ct plus phi of t, where phi of t can be represented for PM system by kp x of t, and for frequency modulation system kf minus infinity to t and x of t dt. This is the integral part. So, and the noise we can represent by n of t is equal to Vn of t cos omega ct plus phi of t, which is to be added onto the channel. So after this part, the signal will combine, it will be combined on the channel, and xc of t, n of t we will get, and after band pass filter, the spectral will become as we have shown in the previous lecture, and there y I of t we can calculate input at the detector state. Detector will combine here, that is a discriminator and low pass filter. So here we'll get the output signal. So y I of t we are getting AC cos omega ct plus phi of t plus Vn of t cos omega ct plus phi n of t, and this here we are getting y I of t is equal to real part of AC e to power j omega ct plus phi of t, and we can represent it plus Vn of t e to power j omega ct phi n of t. These are the real parts indicating, as we know that e to power j theta is equal to cos theta plus j sin theta. So j sin theta is the imaginary part, and here cos theta is the real part. Likewise we have written this is the cos AC cos omega ct plus phi of t. This is the real part of this function, and Vn of t cos omega ct plus phi n of t, this is the real part of this function. So if we take out this e to power j omega ct, it is common, and we can write it like this, that is AC e to power j phi of t plus Vn of t e to power j phi n of t e to power j omega ct. So here we are writing y of t is equal to y of t e to power j omega ct, and where we can write this y of t is the amplitude this. So here we have written it separately. Then we can solve this equation by representing through the vector. So AC is having an angle of phi of t with reference to reference line, and this Vn of t is having a phi n of t angle with reference to this reference line, and Vn of t is the magnitude. So these both are added, vector addition, and we are getting this y of t resultant, and y of t is having theta of t angle with reference to reference line. So this angle between them, theta of t minus phi of t, it becomes, and here it becomes phi n of t minus phi of t. So if you see, this is a small arc, and it is approximately both are same. We have extended it because Vn of t cos of phi n of t minus phi of t, that is very less, but if we add it, then we get AC plus Vn of t cos omega cos of phi n of t minus phi of t, that will have. So this will be acting as a radius, and this will be acting as a arc, and we can find out the angle between them. So theta of t minus phi of t is equal to AB here is arc, and OB is the radius. So we have written it formula, that is angle is equal to arc per radius. So by this, using this formula, we are writing theta of t minus phi of t is equal to Vn of t sin phi n of t minus phi of t divided by AC plus Vn of t cos of phi n of t minus phi of t. So this as a whole quantity is replaced by AC. We are in place of this, we are writing AC, and because this quantity is much more higher than this quantity, that's why we are writing it AC, and Vn of t sin phi n of t minus phi of t. Here phi n of t is phi n of t minus phi of t. This value is approximately equal to phi n of t. So we are writing it, and we are amending this formula as theta. We are amending this formula as theta of t is equal to phi of t plus vn of t sin phi n of t AC. And this vn of t sin phi n of t is nothing but the in phase quadrature phase component of the noise. This is quadrature phase component of the noise. So we are writing theta of t, and this is the output. Theta of t is the output of the detector. So theta of t is equal to y naught of t is equal to phi of t plus, and we are replacing this value of NSS of t AC. This will be used for the phase modulation, and here if we differentiate it this as a whole, then we'll get it for the frequency modulation. D theta by dt is equal to d phi over dt plus 1 by AC and dns of t dt, and here we have written it d theta by dt is equal to d by dt minus infinity to t kf x of t dt plus 1 upon AC ns dash of t. So here we have represented this value by n dash of t. So this is the equation, and here we say that d theta by dt is the output for the frequency modulation system. So we have written it y naught of t is equal to the d theta by dt is equal to kf x of t. It will become, because this integral is compensated by that differentiation. So kf x of t it becomes, and n dash of t divided by AC it becomes. Now we can calculate the noise power and the we can calculate the noise power and the signal power in the FM system and PM system. So let us see for the FM system y naught of t, we are repeating it, kf x of t plus n dash of t divided by AC. We can calculate the power of this. So expectation value of k square f x square of t we are writing, and here kf square we have taken common, and e of x square of t we are assuming it to be sx. And the noise power we can calculate from the previous formula, and we are writing it here, and output noise power is equal to expectation of 1 by AC square and dash s square of t is equal to 1 by AC square e of n dash s square of t, and this we can calculate by this formula. This is expectation of n dash s square of t is equal to 1 by 2 pi minus w to w omega square eta d omega, and if we solve it we can get that eta by eta w cube divided by 3 pi, and if we are writing w is equal to 2 pi b, if we are writing 2 pi b, w is equal to 2 pi b, where b is equal to the modulation signal frequency, and this becomes the formula for the noise power. So if we multiply by 1 by AC square this component, then we can get, so we will get by multiplying this 8 pi square b cube eta by 3 AC square. Now we can have the signal to noise ratio. So signal to noise ratio we can have that signal power, output power is equal to k square f sx we had calculated, n naught we have calculated this, so we have divided it, and we have got this formula 3 kf square sx AC square by 8 pi square b k eta. And if we take consideration of that basement system, then the input signal to noise ratio AC square by 2 eta b is that, and it was referred by gamma factor. So we can separate it and we can write it in terms of that gamma. So 3 kf square sx by 4 pi b cube, here AC square by 2 eta b, and this is replaced by gamma. So if we see this formula, that signal to noise ratio, here if the noise is high, if the noise spectral goes high, then the signal to noise ratio will become high. So the noise is in the denominator term, whereas the signal power is in the numerator terms. So here this is important thing, that the output signal to noise ratio is by far better than other systems. So this is That's why the FM system has less noise. And here we see that is output of the phase modulation system, that is represented by theta t is equal to phi of t plus ns of t AC. And now we can calculate the power. Phi of t we can have a kp x of t by the previous formula, and we can have the average energy as we have previously seen, E of kp square x square of t. E of x square of t we write Sx, and here we are having that value, so 1 by AC square and n square s of t. And if we calculate this energy of that quadrature phase component, then it is equal to, that is power of this average power, E of n square s of t is equal to 1 by 2 pi minus w to w SNS of omega dw d omega. And here SNS of omega is nothing but the eta, so we can integrate it and we have this formula 2 eta w divided by 2 pi. 2 and 2 both are cancelled, and here we can write w equal to 2 pi b. So here we are writing, and we can get this formula, that is this much, and output noise power is equal to 2 eta b divided by AC square. So we can take the again signal to noise ratio from this formula, and we can take this formula here. This is this formula kp square x. Kp square Sx divided by 2 eta b AC square. This becomes the signal to noise ratio at the output of the phase modulation systems receiver side. So here again we want to write in terms of the baseband systems, then we can write kp square Sx, we can separate, and AC square by 2 eta b is the gamma. So we can replace it and we can get this signal to noise ratio for the PM systems. So read them, practice them, and as they are most important, and read it 2 times or 3 times and practice them. Thank you very much.